Hello everyone, welcome to lecture 8 of the online course on modern display technologies, flat panel display. Today's lecture will be on fundamentals of colorimetry and we'll have 2 lectures on this. So in this lecture, here is the lecture outline. We'll go into details of trichromatic space and also we'll try to do the equations that allow us to calculate and go into the depth of the CIE 1931 colorimetric observer. Okay. So, these are the 2 topics that will be covered in this particular lecture. In the next lecture, we will be covering these 3, that is CIE 1976 uniform color system, the basic calculations and methods how you can find a quantifiable difference between 2 observed or perceived colors. You can also, we will also look into CIS CM02 color appearance model and color gamut. So, when you talk about trichromatic space, this is important for color recognition in human eyes, right. So, this basically is a result of stimulation from 3 types of cone cells, which we have just seen in the previous lecture, L, M and S cones, okay. And the colors can be approximately matched by combining red, green and blue lights, okay. So, how color matching is done? Here is an experimental setup that is shown in the figure. So, you see this is a white screen where you have basically placed a black barrier. Okay. So, some arbitrary light basically illuminates the lower half of this white screen. So, some part will get reflected and will go to human eye, and on the upper half what you have? You basically have different light sources to create the same color. So, you are basically viewing it from this particular hole that is created in this black barrier. So, this basically limit the angle of light and focused stimulation on specific photoreceptors. So, on the other half of the white screen, you are basically illuminating, as I mentioned, using red, green and blue light, and the intensities of this light can be adjusted till the mixed up color matches pretty closely with this color that is coming from the arbitrary light. So, who is telling that? Eye is actually sensing that and telling you about when you are getting that match. So, the idea of the color matching experiment is that the stimuli from the upper and the lower half to your L, M and S cones, okay, they should be exactly same, and then you can say that the colors are matched. However, it may happen that their spectra looks different. So, spectra means like the wavelength, there may be higher intensity in different wavelength, but the perceived information but by your eye, the cone cells, they are basically same. So, this is a key principle that the stimuli from the upper and the lower halves of the screen, they basically produce identical response in your L, M and S cones, even if their actual spectra differs. So, with that, now let us introduce this tri-stimulus space of RGB primary colors. So, what we understood that according to the color matching experiment, because there are 3 kinds of cone cells, any stimulus can be basically represented by a vector in a 3-dimensional vector space, and that vector space is called trichromatic space, right. So, 3 cone stimuli, you have 3D vector space. So, you can name them as R, G and B. These are basically representing the red, green and the blue stimuli. Okay. Now, how do you represent any light? Say you have a light Q that can be represented as a linear combination of red, green and blue vectors, right. So, you can have RQ R plus GQ Q plus BQ B, okay. GQG basically, yeah. So, that is basically the Q vector. Normally how you actually do the you have 3 different components for each basic vectors that will sum up and you get the actual vector. Okay. So, these 3 are the tri-stimulus values for red, green and blue. So, this is how you basically represent any color on this trichromatic space. Now, what is this coordinate? This is 1 0 0, this coordinate is 0 0 1 and this one is 0 1 0, right. And another important thing is that if you join these 3 points, you are getting basically a plane on which small r, small g and small b, they basically add up to 1. We will come to this, what are these small quantities. Now, you have to notice one thing, that the wavelengths which are very close in range, something like 630 nanometer and 650 nanometer, both may appear red to a human eye, but they will basically they will be represented by different vectors in this trichromatic space. So, let us take some example tri-stimulus values. So, for example, if you see here the G, okay, in this particular case for Q color, the G is larger than its unit vector itself, because the G value is here, the unit vector was here. Okay. So, the G value is larger than its unit vector, whereas the projection on the RB plane only gives you small value of R and B. Okay. So, that means in this particular case the Q, that particular stimulus Q actually includes a much larger component of green as compared to red and blue. The length of the stimulus Q basically represents the intensity, and longer the length, obviously higher will be the intensity. So, the vector Q basically intersect this particular plane. As I mentioned, there is a plane that you can form by joining these 3 unit vectors. Okay. And this basically represents, this one will represent 1 0 0, that means pure red, this is pure green, this particular point, and this is pure blue. So, you get this plane and this vector is basically intersecting this plane at this particular point, right. So, you can observe that this point is basically closer to this particular unit vector as compared to the other 2 unit vectors. That means, you can tell that this Q will definitely contain more green component, because it is closer to the green unit vector as compared to the other 2, red and blue. Now, coming to these small values, what are these small values? We are basically normalizing them. So, on this plane we get small r, which is capital R divided by capital R plus capital G plus capital B. Similarly, small g will be capital G divided by again the sum of RGB. Small b will be B divided by the sum of RGB, and this all the small quantities, small r plus small g plus small b, will be equal to 1. So, here each point in this triangle basically represents a very distinct color, and the line which links the blue and the red point, basically this one, is allowing you the color mixing between the 2 colors, red and blue. So, any line between these 2 will allow color mixing between blue and green. Anything here, the color mixing will happen between green and red. And when you have anything in between in this triangle, so you are basically mixing all the 3 colors, red, green and blue. However, in some cases it may happen that one cannot obtain a matched color, okay, no matter how the RGB, the capital RGB intensities are adjusted. It is basically possible to move, in such cases you can move one of the primaries, for example, the red one, from the opposite to the same side of the barrier as the color being matched. That means, you basically wanted to match Q equals RQR plus GQG plus BQB. Instead of doing that, you basically move the red to the same side of the barrier. So, you basically start getting a negative tri-stimulus value. With that you are able to match the color. So, here the basic idea of the color matching experiment was to produce the stimulus to the different types of cone cells, right. The L, M and S cones, which are basically sensitive to red, green and blue light, and it can be matched to any arbitrary light intensity that can be done by varying the intensity of those lights. So, what people have seen in CIE 1931 standard observer or colorimetric observer, okay, that this particular method used 3 primary colors which have wavelengths at 700 nanometer, 546.1 nanometer and 435.8 nanometer. They can match all the visible monochromatic lights, okay, and that is basically called the CIE 1931 capital R, capital G, capital B, RGB system. So, mathematically in this case a spectrum can be expressed as a superposition of monochromatic units. Hence, a broad light can be viewing by mixing many of the monochromatic components together. Now, to obtain the coordinates of each color, the first step is to obtain the RGB stimulus of the monochromatic light. So, here we can introduce the equal energy spectrum, which is E, with some constant optical power described in terms of watts for all the wavelengths. So, you can actually have E, which is integration of E lambda d lambda. So, what is E lambda? That is basically the monochromatic component of this, but you are basically integrating over different lambdas to get the equal energy spectrum E. So, E lambda is used as the matched monochromatic light for color matching experiment, and hence its intensity can be kept constant in terms of the radiometry unit, that is watt. So, what we understood is that we can have E lambda, which is basically R lambda bar plus G bar lambda G plus B bar lambda B. So, here basically you can see that these are basically the stimulus at a given wavelength lambda. Okay. So, this is the blue one, this is the green one and this is the red one. So, these are the tri-stimulus values for different wavelengths. Okay. So, this R bar lambda, G bar lambda and B bar lambda are the tri-stimulus values with the stimulus E lambda at wavelength lambda. So, when you normalize this, that means you consider R bar lambda plus G bar lambda plus B bar lambda equals 1 at different wavelengths. Okay. We basically can obtain this CIE 1931 RGB chromaticity diagram, which is shown here. So, here you see you have only 2 coordinates, one is small r, one is small g, because once you know these two, you always know this B component, because that will be simply 1 minus r minus g. Now, due to the linear summation of different color stimuli, a spectrum with many different wavelengths can basically be subdivided into monochromatic lights and can be viewed as the color mixing of each monochromatic component. So, in this you can see we are basically starting from 380, that is blue, and along this perimeter of this periphery of this horseshoe kind of chromatic diagram, we are having different monochromatic wavelengths going up to red, that is 700, corresponding to R equals 1, and other two will be 0 0 obviously. Here this one R is also 0, G is also 0. So, you have pure blue at 380 nanometer. So, any color can be represented within this horseshoe shaped region, and as I mentioned, this is basically formed by the monochromatic light locus and there is a connection between this 380 and 780 nanometer. This is not 700, 780 nanometer wavelength. Besides, you can also note that in this particular color system, the R bar lambda values are negative. So, you can actually have these values to be negative. So, they are matched when basically your wavelength lies from around 435.8 nanometer till here, which is around 546.1 nanometer. So, for matching these wavelengths, you need the value of R or R bar lambda to be negative. Okay. So, in this particular figure, we have used these negative R values when describing some colors, but it does not look very good because you have some negative values here. So, to improve this situation, instead of using RGB CIE 1931 XYZ system was proposed. So, you are basically now making some linear transformation from your RGB system to XYZ system within this 1931 colorimetric space, so that this negative values can be avoided. So, this XYZ coordinates are basically obtained through linear transformation of the CIE 1931 RGB system, and these are the equations that correlate these two parameters. So, X, Y, Z, the small ones correspond to these small RGB values using these equations. I will not read it out, you can use these equations. So, what happens? You have now transformed to small x and small y, okay? Z will be related again. So, that way both the values are now positive. So, you can see the small x basically goes from 0 to 0.8 and y value goes from 0 to 0.9. Okay. So, you basically obtain this CIE 1931 XYZ chromaticity diagram, which is shown here. So, in this particular system also, the chromaticity diagram looks like this horseshoe that basically now lies in the first quadrant, which means all the colors can now be described using positive coordinates, right. Now, in those equations we understood, we got small x, y, z. So, what are these values of capital X, Y, Z in this colored system? So, here you have to remember that the y, capital Y value is basically set equal to the luminance of the stimulus, okay, which has got a unit of candela per meter square. Okay. So, V represents luminance for this stimulus. So, you can obtain capital X as small x by y times V. Capital Y is basically your luminance value. Okay. So, you are using the green one, or you can say the capital Y for luminance, and capital Z can be obtained as small z by y into V. Okay. Now, we obtained this capital X, capital Y and capital Z. Now, you can also obtain this CIE 1931 XYZ color coordinates, okay, from a spectrum. So, in that case you can use these equations that basically rely on linear summation. So, integration is nothing but summation of the tri-stimuli values that you obtain for each wavelength. So, you basically integrate it over lambda. So, you write it as P lambda. P lambda is basically the spectral distribution of the stimulus, which is given in terms of watt per steradian meter square, okay, steradian meter square, okay, and this is how it is calculated. So, capital X equals K integration over lambda P lambda x per lambda d lambda. Similarly, capital Y and capital Z can be calculated, and the small x and small y are now obtained as this. So, it is capital X divided by the sum of capital X, capital Y and capital Z. Y is also calculated like this. So, what is K here? Is K is basically 683 lumen per watt, which basically represents the unit transformation from radiometry to photometry. So, radiometry calculates it in watt, in photometry we basically go to lumen. So, this is a constant that basically does the unit transformation. So, its unit itself is 683 lumen per watt. Okay, and P lambda will have this watt, so they will cancel out and you get everything in photometry unit. Wonderful. So, now let us look into some example, okay, of this 1931 colorimetric observer. Okay. So, let us try to find the luminance and color coordinates of the mixture of the two color stimuli that is given here. So, you have two stimulus given to you, one is stimulus 1 and stimulus 2, and these are the small x small y value of the two stimulus. So, these are basically two colors, right, they are having these two stimulus and you want to mix them. So, you want to find out what will be the luminance and the color coordinate for the mixture of these two colors. Okay. And the luminance unit is in nits. The first stimulus has luminance of 30 and the other one has got 21. So, one thing we can simply say, when you mix two colors, their luminance will simply add up. So, it will become 51. We will see as a proof later on as well. So, now let us first, because these are given in the small x small y unit. So, let us first try to see, because we have to go to the capital X values to basically find out and add them up, right. This is the normal edge value. So, we can use this equation. We know that capital X is basically small x by small y into V, V is the luminance, okay, y equals V, and capital Z is basically small z over y into V. So, if you actually do capital X by small x, you get V by y, okay. That is same as if you do this capital Y by small y, you again get V by y. If you do capital Z by small z, you get V by y, okay. So, this three becomes same, okay, if you divide this like this. So, what you get, you are basically can say that this is equal to x plus y plus z, okay. So, from this, so in the first stimulus, so this value is small x, okay. So, you take capital X1 divided by small x, that will be equal to, so V equals y, so you can actually take this y by small y, okay. So, this is y 30 divided by small y, which will be equal to capital Z1 divided by, because these three things should add up to 1. So, small z is 0.1, because this is 0.6, 0.3 adding up to 0.9. So, small z is basically 0.1. So, from this you can basically find out what is your capital X1 and you can find out what is your capital Z1. Similarly, for the second stimulus, you can see small x is 0.2, small y is 0.7. So, what will be small z? Again 1 minus 0.2 minus 0.7, that is 0.1. So, for this you can again write x2 divided by 0.2, that will be equal to 21, that is the value of capital Y, because that is V luminance. So, 21 divided by small y, okay, that will be same as Z2 divided by small z, which is 0.1. So, from this if you do very simple maths, you get x1 equals 60, z1 equal 10. From the second equation, you get x2 equals 6, z2 equals 3. So, when you mix these two colors, what will happen? X1 and x2 will get added up, okay. So, you will get capital X, which is now x1 plus x2, that is giving you 60 plus 6, 66, okay. Similarly, you can add up y, okay, that is y1 plus y2, that will give you 30 plus 21, that is 51, okay, and capital Z will be Z1 plus Z2, that is 10 plus 3 equals 13. So, once you know capital X plus capital Y plus capital Z can be found out, So that goes in the denominator, numerator is capital X, that gives you the new small x of the mixture. So that is basically 66 divided by 130, that is 0.51. Similarly, you can find out what is small y, that is capital Y divided by, so capital Y is basically 51 of the mixture, divided by this summation, which is basically 130, that is 0.39. So when you mix these two stimulus, that is basically you are mixing the two colors, okay, that is basically giving you a new stimulus, okay, which is having coordinates of 0.51 and 0.39. And what is the luminance in nits? That is 51 units. I believe you understood how it is done. So this is how and this is why people have actually moved from CIE 1931 RGB to CIE 1931 XYZ space, so that all the normalized values or the coordinates of the trichromatic space are positive, okay, or they are in the first quadrant, but because that makes your calculation and life easy. So with that we conclude our lecture. So if you have got any query regarding this lecture, you can always drop an email to this particular email address mentioning the course name on the subject line. Thank you for your attention.